Hello, welcome to another cosmology talk. Today we have Dan Thomas, who is a postdoc at Queen Mary University, London. He'll be talking today about a paper that is simulating modified gravity in about as model-independent way as you possibly can. Although obviously there's always going to be some models that aren't captured and things like that. And to actually do the final simulation, you need to set some conditions. People interested in modified gravity should be interested, as these guys probably have the tool you want to look at nonlinear stuff in your model. And everyone else, perhaps especially observers, should pay attention, as this is one of the good ways that constraints will be able to be applied to all of these modified gravity models. The nonlinear stuff has lots of information, and Dan and his collaborators are the ones that can get at that information. So thanks for coming, Dan. And do you want to give us a brief summary of what it is that you did in the paper?
Yeah, so exactly as you say, right? The model independent is kind of the key phrase. So we've come up with a way to put model-independent constraints on modified gravity using data from all the scales that our future surveys are going to be able to access. So perhaps I should say something just briefly so model independence is, just trying to say something generically about departures from general relativity. So without having to, pick a model, choose some field content, or, whatever way you normally specify your model, try and avoid that problem.
If people are remembering this talk or your paper a couple of months from now, and there's only two things they remember, what would those two things be?
Yeah, so I think a good general one is just that, if we have intuition in a lambda CDM general relativity cosmology, it doesn't necessarily port over to an alternative cosmology. So that's kind of a general one, if you like, which of course appears in other contexts. Specifically for our stuff, it's that we have this framework, right, from doing model independent modified gravity on all scales, but we've also started doing practical things with that framework and looking at the simulations and the fitting functions. So we've taken a good couple of steps getting towards actual data analysis with this framework.
Why did you do this specific stuff in this particular paper? What was unsolved that needed to be solved? Why did it happen in 2021 and not 2018?
Yeah, so let me sort of sketch a little cartoon first, and then I'll give a few more details. So I think there's been a bit of an elephant in the room. So we've got these sort of powerful upcoming surveys, the Euclid satellite, the legacy survey of space and time on the Vera Rubin Observatory, really powerful surveys coming up with lots of data. And we want to learn about gravity from them, but most of our tools for looking at modified gravity, and particularly in a model-independent way, only work on the linear scales, which is less than half of the scales where we're going to have data from these things. So I think there's been this elephant in the room, really. I mean, I had conversations back more than a decade ago with people about this issue. So we do have some specific theories that we look at and that we have tools to do, the nonlinear stuff with. But at the risk of being perhaps a bit provocative, I think those theories are getting a bit creaky. They already have quite a lot of constraining power on them. And so I think one can ask, well, what are we actually going to learn about gravity from these upcoming surveys? We might just end up, worst case scenario, and again, being deliberately a bit provocative here, we might just end up ruling out some theories that are kind of dead already. So I guess that's the cartoon version. So what I was going to do was give you a couple of slides doing it sort of in a touch more detail. Okay, so this is my attempt to summarize 15 years' work in one slide from lots of people. So I hope no one's offended that there are no references on this slide, but it's a really substantial body of literature now. And as I say, many authors, most continents over 15 years or so. So this is like a whistle-stop tour of where we're at with model-independent modified gravity in cosmology. And the basic story is these two equations here. So we have something like a Poisson equation relating one of the gravitational potentials to the density. And then in that, we put this kind of possibly time and space dependent alternative strength of gravity here. This is like a time and space dependent Newton's constant. And then we have a second equation which relates the two scalar potentials. So we know that in general relativity, as opposed to Newtonian gravity, we have two scalar potentials rather than one. But most of the time in GR in cosmology, they actually wind up being the same. But what we allow here is for the modified gravity to create some sort of time and space dependent difference between the two potentials. And as I say, this has sort of been studied for 15 years. It's kind of well understood in what circumstances it applies, which theories it applies to. We know it's quite general. And of course, we resort to general relativity when mu is 1 and eta is 1.
I guess just being a pedant, it's in general relativity and in FRW metric that mu equals 1 and eta equals 1, I guess.
Yeah, so this is, linear cosmological perturbation theory, FRW metric. Yeah. But yes, kind of standard cosmology thing, yeah. Because there's also no vectors and tensors here, right? And I'll touch on that in a minute. And then sort of observationally, the sort of conventional wisdom is that you want to constrain these things by combining two different kinds of observables. One that depends on basically photon trajectories, so something like gravitational lensing, which is the sum of the potentials, or integrated Sachs-Wolf from the CMB, which has the time derivatives. And then combine that with something that has one potential, right? So this normally means non-relativistic matter and the clustering of non-relativistic matter. So, the matter power spectrum, the growth rate of structure, this type of thing. And so this is sort of where we're at after 15 years. And this is all well known, well understood, well studied, and so on and so on. So what's the problem with it? Well, as I said, the problem is that we have these powerful upcoming surveys, but for most of the scales that the surveys are going to take data on, the kind of assumptions that go into getting to these equations, primarily the perturbation theory assumptions, just no longer apply. And so what we're going to end up doing is throwing most of the data away. And I actually have a plot later on to give you an idea of how much we're really throwing away. And so this is kind of back to that sort of provocative question I asked you, how much are we actually going to learn from these surveys about gravity? So that's kind of, if you like, the problem keeping me up at night. And then possibly a clue to the path forward, right? In the sense that what do we do on small scales where we can't use perturbation theory? Well, we run n-body simulations. And of course, you can look at in your n-body simulation and you see a Poisson equation. And so kind of the obvious question to ask then is, can I do something like what I did with this Poisson equation, but do it with the one in my n-body simulation? And actually, this is so obvious that a bunch of different groups started doing it at around the same time that people were working on the linear theory stuff. But then interest dropped off. It's kind of just completely waned. And I think what happened here is it's not that doing this is wrong, but it's kind of a bit unclear what you're doing. So, how well motivated or consistent is it to do this? And actually, in terms of the interpretation, how do you relate it to the linear parameterizations and to which modified gravity theories and under what conditions does it apply? That's all kind of a bit unclear if we do this. Sort of a corollary related to these two is this thing about degrees of freedom in the metric. We said a second ago that it's well understood in perturbation theory when, where, and why we can just worry about the two scalar potentials and neglect the two vector and the two tensor degrees of freedom in the metric. And at the time these works were done, these sort of early modified gravity and body simulations were done, I think the situation was much less clear about the vectors and tensors. And so one of the things we've learned a lot about as a community since these early modified gravity and body things is about the Newtonian limit in cosmology, testing n-body simulations, and building towards relativistic simulations. And so this is not exhaustive at all, but it's just a few references, a few of the different groups that have worked on this. But basically, the kind of spoiler alert is that actually this Poisson equation is not a red herring. And actually, with what we've learned about the Newtonian limit, we can build something that's going to work on a much bigger range of scales. So that's sort of the problem and the context and the motivation.
Cool. So in that case, do you want to get into the details of the actual paper?
Yeah, so what I'll do is, because there's a theory paper and then a simulation paper. So I think the theory paper and the idea has more of the interest. So I'll spend a bit longer on that, and then I'll come to the simulations and we can see how it works in practice. But first, what I want to do is let's just forget modified gravity. Okay, let's just go back to our GR, lambda CDM cosmology and think about how that works. So how do cosmologists think about gravity and how do cosmologists do gravitational calculations? So this bar here is my attempt to represent this. So this bar represents the different scales in the universe. So on the left-hand side, we've got the large scales, and on the right-hand side, we've got the small scales. And so we've got some horizon here. And then, of course, on small scales, we have some point below which we shouldn't really talk about cosmology at all. And then an important scale here is the nonlinear scale. So the idea here is just that, okay, above that scale, your density fluctuations are generally small, and below that scale, they're allowed to be large. And so from that scale upwards is sort of the regime of validity of our perturbation theory, our sort of standard tool. And that, of course, is the regime of validity of that earlier model independent stuff I was talking about. And then on small scales, we have our Newtonian stuff valid up to some Newtonian scale. And something that's not really talked about explicitly is the some intermediate regime, is the some regime in which neither of these two limits actually applies. And then sort of another, I think something that's quite interesting about these two limits is in principle, they're very different. And I'll be a bit more concrete about this in a second, but in principle, they're very different. And in practice, you get something very similar in the two limits, right? Which I think is worthy of study in and of itself. So just let me be slightly more concrete about that. So on the large scales in our perturbation theory, how does it work? Well, we have all our fluctuations in our matter and in our metric, and we say they're all small and they're all the same order of smallness. And then on top of that, we have our various gauge choices for those that know about perturbation theory. And we also have this quite clear scale of split. So basically, all those things I've just said are not true in the small scale limit. Most of the gauges we use on large scales, we can't apply. We're dealing with Newtonian potentials, not linearized potentials. All the quantities now have different smallness. So a velocity and a gravitational potential would be differently small. And of course, most importantly, the density can be large, and not just larger than the other perturbations, but just outright large. And so in principle, as I say, these two limits are really, really quite different. And in practice, of course, what do we get? We get an equation saying the two potentials are the same, and we get a Poisson equation in each limit, despite all these differences. Now, the Poisson equations are slightly different. So the Newtonian one on the right here, the density can be arbitrarily large in some sense. Whereas the large scale perturbation theory Poisson equation, not only is the density required to be small, but it has a slightly funny definition. So this big delta here, for those that know about these things, I just mean a gauge invariant density. So we have to define the density in a specific way for it to make sense on the largest scales. And so I think most cosmologists have the intuition that, well, look, I've got a Poisson equation and an equation relating the potentials on large scales. I've got the same on small scales. So, surely the same thing is really happening in both limits, right? It's the same dynamics, the same degree of freedom. And so sort of the questions that got me thinking to start with were, can we be more concrete about this idea that we've got the same thing going on in the two limits? And also in the process of that, can we address this possible intermediate regime?
And I guess there's also the interesting possibility that even if in lambda CDM, they do give the same predictions, that in a modified gravity scenario, they might not.
Exactly. And it's not even necessarily modified gravity, right? For example, I'll do a quick aside here. If you have a radiation dominated lambda CDM universe, everything I'm talking about doesn't apply because you can't use the Newtonian limit on small scales, right? So I'm talking about a matter and lambda dominated lambda CDM universe. Okay, so then to come to your question of why is this work happening nowish? So I've got two kind of ingredients that are what I'm going to put together here. So the first is this post-Friedman formalism, and I'll say a bit more about this in a sec. But this was developed by Marco Bruni with a PhD student and a couple of collaborators at Portsmouth. And this is the archive number here for anyone that's sort of interested. And then the second ingredient is what I mentioned before about all these lessons. We've learned about the Newtonian limit, we've learned about relativistic simulations and so on and so on. And the key lesson from all those things, at least for the purpose of what I'm talking about today, is that there is no intermediate regime in lambda CDM. Okay, there is no range of scales where neither your Newtonian limit or your perturbation theory applies. And again, I think this is quite intuitive for people, but at least it's concretely, robustly, quantitatively checked now, right? Okay. So this post-Friedman formalism, so the equations are just there to scare people. I am not expecting anyone on YouTube to go through these equations term by term. They are literally just there to scare people, and we'll get to them in a second. So this is like, a sort of post-Newtonian style 1/c expansion, right? Much like what people use in, the solar system or whatever, but just designed to work in cosmology. And the nice thing about it is you get some sort of master equations that work in the Newtonian limit, that work in the linear theory limit, and also can describe a possible intermediate regime. And in doing this, they have this weak field variable, essentially, which Marco calls the resummed potentials. And that kind of makes manifest that earlier intuition that the same thing is going on all scales. So we can define a gravitational potential that kind of is the thing that is operating on all scales. Okay, so this sounds really wonderful. Why is this not just instantly the result we need? Well, now we look at the equations and we say, okay, what am I going to do with these, right? These are horrible equations. I'm never going to be able to solve these or do anything useful with them. And it's fine. I've already apologized to Marco. He knows I say that about his equations. So then really the question is, can we simplify them? And of course, the answer is going to be yes. Otherwise, I wouldn't be here. So it turns out that most of the complexity in these equations is required in order to describe the intermediate regime. So what I can do is sort of schematically bundle together into this piece here all of the terms that only matter in the intermediate regime. Now that means terms that are both higher order in the 1/c expansion, or what I call structurally nonlinear. So this is just some vocabulary I've invented. So something like phi squared or the density contrast times the velocity. to distinguish it just from, for example, the density by itself, which can be nonlinear in the sense of being large, but isn't of the structurally nonlinear form. So we bundle all of these terms into this bit here. And look, we've already got something really indicative happening here, right? So what have we got if we look at the rest of the equation we've got left now? We've got a k squared times the potential and a right-hand side that is just basically that gauge invariant density from linear theory, except that the density is no longer required to be small. So we're basically back to a Poisson equation. We're not quite there yet because we've still got these terms there. I've just pointed out that they all kind of have the same schematic form.
So can you unpack this term on the far right a little bit? So theta is what?
Sorry, yeah. So theta is the velocity divergence. Basically, these two, the velocity divergence and the density in the gauge I'm in, add together to give a gauge invariant density on super horizon scales. So this is just basically a gauge invariant density contrast.
Is this higher order in the 1 over c squared, or is it just that the theta is sort of carrying the extra c squared and it's the same order in 1 over c squared?
Yeah, so at this point, I'm at mixed orders in the 1 over c squared. So one of the things that the post-Friedmann approach does is it doesn't solve order by order. What it does is it goes up to 1 over c to the 4, and then introduces these weak field variables, and then that is the set of equations you solve. You don't solve 1 over c squared and then plug that into 1 over c to the 4th. And that's why this all works, actually.
And you don't need to worry about 1 over c to the 6th because the weak field limit guarantees they'll all be small, or at least small compared to earlier terms?
Yeah, exactly. So you'd have to worry about higher things. So I'm only going to go as far as the power spectrum when we get to things later on, right? So, of course, everything I've said about, being able to work with these two limits on all scales kind of has some implicit precision and set of observables attached to it, right? Because even in perturbation theory, we know there are things where we have to go beyond linear order, even in the places where it's a very good limit. Yeah, so the second ingredient, of course, that I mentioned was there is no intermediate regime in a lambda CDM cosmology. Boom, job done. So now what we have is some simple equations that looks like a Poisson equation, but to get to it, we haven't taken either of the two limits. So we have something now that applies on all scales. And so we have two simple equations that apply on all scales. It doesn't require the density fluctuation to be small. It contains our large and small scale limits as we expect. And so we've really sort of made, manifest this intuition that we think it's the same thing going on all scales. And surprising nobody, the equations we get are an equation relating the two potentials and something that's basically a Poisson equation. So this is just a curiosity at this point, right? I mean, yes, there are things you can do with them even in a lambda CDM context, but really all it's doing is repackaging a lot of information we already had from other places. And that's kind of implicit in how we do the different calculations and how we tie them all together.
One would still need to be a little careful. I mean, I'm not saying you're not being careful. I'm just meaning if someone misinterpreted your words a bit, that it is true that on the large scales, there are equations that resemble the ones in the small scale Newtonian stuff. But say in a particular gauge, in the Newtonian gauge or something, it's not a one-to-one correspondence between the two phi's in that. It has to be this particular gauge invariant variable you're looking at. So if you're solving the large scale stuff and you want to, initialize your simulation on small scales and not make any mistakes. Maybe everything's so small that you're not going to make a mistake anyway. But if you don't want to make any mistakes, you do need to be a little bit careful that you're initializing the right correspondence between the two. So there is a correspondence, but one has to be careful to get the right one, I guess is what I'm saying.
Yeah, so there's a lot of work on this. Again, actually, quite a lot coming out the ICG at Portsmouth as well with sort of David Wands and his collaborators, right? So they've defined something they call an n-body gauge. And they make very explicit the stuff you're talking about. But actually, for my equations, essentially, this equation works, right? So this equation is in a Poisson gauge, which is a Newtonian gauge, but also with the vector gauge fixed to be on the 0i part of the metric. And in Poisson gauge, this is correct, right? You don't need to adjust it any further, even for the larger scales.
I think the very first ever cosmology talk by Kit Gallagher, who was a PhD student at Queen Mary, I guess he's graduated now. He was going into a lot of detail on all of this. I can't promise if someone goes to watch that talk that it'll be super polished, given it was the first ever one, but it certainly goes into very gory details of this stuff.
Yep, absolutely. So yeah, as I say, this is sort of a curiosity at this point, right? But I'm sure, everyone watching is very smart. They've put two and two together. They've seen exactly where I'm about to go with this. Let's use these two equations for modified gravity on all scales in a model independent way, right? So we can take this sort of all scales Poisson equation and put in some time and space dependent strength of gravity here. And we can take our sort of all scale slip equation and put in a time and space difference between the potentials. But the important thing really is that we didn't just pull these equations out of thin air. We went through quite a careful process to understand how and why they apply. And what that means is we had a set of tests that we can apply to a modified gravity theory. So we now understand to which theories, when and why, and under what conditions this process will apply. So I do go through this in some gory detail in the paper with sort of quite a comprehensive set of checks. I'm not going to go through that now, but basically, most of it amounts to checking, is there an intermediate regime in this cosmology? And if there is no such intermediate regime in your modified gravity cosmology, it should be described by some Poisson equation and some slip equation on all the scales we care about cosmologically. And the nice thing is, not only do we know what these tests are and know how to apply them, but the popular Hughes-Savitzky F of R gravity model, which is a sort of standard one that people worry about in cosmology, has already been shown to fit into this approach because of some work done with essentially the Newtonian limit in that cosmology and so on and so on.
You said that the popular Hughes-Savitzky one that people care about. Why is it popular and why do people care about it over other ones?
Well, it was one of the first ones that kind of was shown to be able to basically do a lambda CDM background and have a screening mechanism on small scales. And so it was one of the first that went, look, you could basically can't rule it out with the normal tests, so let's do the perturbation theory properly. And it is one of the ones that people are simulating in detail for things like the Euclid satellite and so on and so on. So that's sort of everything I wanted to say about the framework. So this is the theory, the idea, how these equations come about and the intuition about them. Of course, at that point, it's still not useful to these surveys, right? So we need to start doing something with some simulations and building towards something that's useful for data analysis. So I'll now just say a few things about that. So this is work led by a PhD student, Shankar at Manchester. So he's done some really cool work on this. So obviously these mu functions could have almost arbitrary freedom on some level, right? And I've sort of swept that under the carpet with everything I've said so far. In linear theory, it puts such strong constraints on what the theories are allowed to do that these things are typically very simple. That is no longer going to be the case on nonlinear scales. And I can show you some functional forms afterwards. Actually, people have looked a little bit and they're simpler than we might naively expect, but in principle, they could be very complicated. So we decided to start with to just remove the scale dependence and look at some time dependence, because this is simpler, but also it's going to allow us to connect with linear theory better and subtract the kind of linear theory out the simulations so we can really focus on the nonlinear bit. And so what we did was we set up some sort of sets of 7 simulations. So we have one simulation where the mu function has a single value for the whole simulation, and then 2 in each of which it's switched on for half of the simulation, and then 4 simulations in each of which it's switched on for a quarter of the simulation. So turning it on for a single interval and then turning it back off again, okay, just as a simple starting point to look at the phenomenology.
And is this something you're doing literally just to see what the consequences are, or are these kind of well motivated based on models that are underlying it?
Yeah, there are theories that we know don't have any scale dependence in mu on nonlinear scales. So any theory that fits into the PPN approach in the solar system actually doesn't have any scale dependence on nonlinear cosmological scales. But primarily this is let's get the simulations working. Let's understand the phenomenology. We're not trying to design these mu functions such that they have the most constraining power in surveys or anything like that. It's just let's take a first step and see what happens.
You have to take the first step somehow. So you said there are some that aren't scale dependent on nonlinear scales. That seems intuitively tricky to me, because I thought the reason mu is changing is it must be somehow related to the local density or something like that, and the global density is decreasing because we're in an expanding universe, but then locally the densities are also, once they go nonlinear, drastically different. So is there some other reason why mu is changing in time? Does it have like some clock attached to it that it knows how long it's been going for, or?
Yeah, so you're thinking of like an F of R type setup where you have some, screening mechanism with some environment or something like this, right? If you dial back to something simpler, something like Brans-Dicke, then you have that background scalar field, which has a background value which changes as your universe evolves, and something like that, which fits into ppn, has a time-dependent mu. It has a scale-dependent transition, but that happens on linear scales.
Okay. When you say it has a time-dependent mu, is that because it's got its own clock, like it's a scalar field rolling down a hill or something like that, or?
Yeah, so just because the modification to g effective in the Poisson equation in that case, to the mu function, comes from the background value of the scalar field for Brown-Sticky. And so as that background scalar field evolves, it means you must be away from GR, right? So in Brown-Sticky, the closer you are to GR, the more that background scalar field kind of freezes out and does nothing.
Okay. So yeah, so that scalar field in nonlinear regions is not taking on drastically different values to the background. I guess that's the crucial thing that.
Yeah, basically, yeah, because it fits into the ppn approach, right? Something like f of r doesn't fit into the ppn approach, right? So the statement I've made there doesn't apply. But so Lucas Lombrais has done some really cool work where he looks at screening mechanisms in spherical collapse and uses this to motivate small scale modifications to the Poisson equation. And so in my framework, that gets reinterpreted as the mu. And he's shown that actually with a relatively simple functional forms, you can actually capture f of r as well. But that one does have scale dependence.
I guess I also have kind of in the back of my mind, and maybe this isn't interesting to you, but maybe it is, but this kind of doing away with dark matter on the small scales, Milgromian Mond sort of stuff, where they also have a, what do they call it, like the environmental dependence or something. I mean, it looks like it would fit exactly into your framework. It would just be the behavior of mu would be very specifically defined by its local environment.
Yes and no. I am looking at applying a lot of what I've done to some theories with Mond, because what they allow you to do is, so there's a missing piece with sort of Mondian type theories, which again is stitching together the cosmological perturbation theory and the astrophysics, right? And no one's really stitched those together properly yet. They sort of work in different regimes of the theory and hope that it's okay. And actually, I've done some work with a friend showing that we can actually use this approach to stitch those together for Mondian theories, but it's not published yet. But for what I'm about to talk about, I can't refer to that stuff because I'm going to run some dark matter n-body simulations. So of course, at that point, it now doesn't apply to Mondian type stuff.
Oh, sure. I mean, not in a literal sense, but some of the sort of qualitative things might be similar, because dark matter and baryonic matter are the same in your simulation. You've just got a lot more matter, I guess, than they would want to have.
So they're only the same if you're turning off all the problematic aspects of the baryons, right?
Are you not doing that? Are you?
No, I'm going to do that, but that's my point, is that for Mond simulations, you kind of have to run with all the baryon stuff turned on, really, I think.
Yeah, I guess because you're on sufficiently small scales that they're relevant.
Yeah. Anyway, so these 7 simulations are chosen such that on linear scale, so at redshift 0, at the end of the simulation, the linear matter power spectra is equal in all 7 simulations. So this will allow us to disentangle the linear theory of it. So I'll quickly show you some of the phenomenology. So this is a ratio of the modified gravity matter power spectrum to the lambda CDM matter power spectrum at redshift 0 when you've run from the same initial conditions. And each colored line is different modified gravity. So it means the modified gravity was turned on at different times. And of course, on linear scales, we get exactly what we would expect. We just get some boost compared to lambda CDM, some value, that's above 1. And then we have this sort of quasi-linear regime. So what's going on in the quasi-linear regime is that your linear matter power spectrum is still the important object, but its effect is getting boosted. Okay, so you get even more extra growth here than what you got on linear scales. And you can see that still it doesn't matter that much which simulation you're in. But then on nonlinear scales, we now have a much bigger difference. So this is saying that your matter power spectrum at redshift 0 has some memory of at what point in time the modified gravity effects were turned on. And this is because it's meddling with the really sort of nonlinear aspects of halo formation, right? So you're changing the times at which halos form, which mass of halos are forming at different times. You're changing your background density at the point at which halos form. So therefore, you're changing the halo concentration. So you're really meddling with the really nonlinear stuff. And that's why it has this memory here on smaller scales.
As you said, this is the first step, so one takes small steps, but you would also want to be including baryons before you're actually saying anything on these scales, anything super meaningful about our observable universe.
Yeah, absolutely. And yeah, if you want to criticize my work or in a nice way preempt what the next step is, of course baryons has to be in there, right? Baryons is the buzzword for these upcoming surveys on some level, basically, right? If we can't do baryonification, we're still throwing most of the data away anyway. Okay, so that's sort of the matter power spectrum. So what about lensing observables? These will be important observables for these surveys. So this plot on the left is kind of showing that thing I said in the motivation about how much data are we going to throw away. So this is just some weak lensing observables. For those that care about the details, it's the lowest redshift tomographic bin for a Euclid-like survey. The red line is a lambda CDM prediction with the approximate error bars for the survey. And the black is our approach using one of our simulations. And then this blue line here is one of the linear theory approaches. And you can see you have to truncate the linear theory approach because it runs out of its regime of validity. And so, again, this is what I mean. All the data here is getting thrown away if we use these linear theory approaches. And all we're left with is a small range of scales. Not only is it a small range of scales, it's also where the error bars are largest. So this is not new news. Everyone knows that nonlinearities matter for lensing in these surveys. We're just showing it quantitatively in our context. But it just gives you an idea, really, how much data we're going to throw away if we just stick with these linear theory approaches. Okay, so I've mentioned mu a few times as the strength of gravity in the simulations. I haven't mentioned the eta. The nice thing about how we've set the parameterization up is that we don't need to worry about eta while we're running the simulations. We only need to worry about it when we're post-processing for certain observables, which includes lensing.
Is that because the psi variable doesn't actually affect the clustering? It would just affect like the passage of light or something like that?
Yeah, so I did some sleight of hand without telling you, right? It's the same thing that's done on linear scales. So this, where am I? This is the Poisson equation in GR, and it has a psi in it. And then when I did it with modified gravity, I changed it to a phi. Because basically you can do this, right? It's the same thing on linear theory. Because you're now working with a parameterized Poisson equation, you can do this. But what the advantage of this choice is that now, because phi is the potential that determines your non-relativistic matter, as you say, then your simulation only depends on this equation, and you completely ignore the slip equation for the purposes of the simulation, because you're not evolving any photons in it, as you say, right? It's purely non-relativistic matter.
But then you are, of course, evolving photons when you talk about stuff that our telescopes detect, because they're detecting light. But that's what you're saying. You can do it as a post-processing thing. Okay.
Yeah, exactly. So this sort of lensing equation, which is how you calculate these lensing observables. Don't pay too much attention to the details. Just want to draw your attention to how the modified gravity turns up in this equation. So you have an explicit mu and eta in this term here. And this is why sometimes you see that capital sigma parameterization. That's exactly doing this piece here. But then there's also in the matter power spectrum, we have the effect of mu as well. Now in linear theory, that mostly just shifts the matter power spectrum up and down. So we get this kind of almost total degeneracy between the mu and eta in linear theory. But we've just seen that in nonlinear scales, we can get a scale dependence from the mu. And that's what we're showing in this plot here. So each of these lines are different choices of mu and eta. And basically the point is that if you look at any two lines that are similar on these scales, they'll now be different on these scales and vice versa. So this scale dependence we're getting in the matter power spectrum is actually allowing us to break this degeneracy that exists in linear theory. And so that's another little cool thing that we don't get in just in the purely linear theory.
And so eta here was then turned on, I guess I can read in the caption, from 0 to 7.01.
Yeah, that's just, it's one of the 4 bins. So it's only turned on for the final quarter of the simulation, basically, which is redshift 0 to 7. It's not a quarter of the redshift of the simulation because we match the lambda CDM growth. So the point is that in lambda CDM from redshift 0 to 7, you get a quarter of the growth you get from redshift 0 to 50. So that's why it is that value. Okay, now everything I've said so far is just some cool output of the simulations. We can't run embodied simulations as part of our data analysis pipelines, right? They are far, far, far too computationally expensive. And that's where these things called fitting functions come in, right? So what we need is some way we kind of capture the output of our simulations accurately with some kind of semi-analytic formula or something, which saves us having to run these expensive embodied simulations. And so the other sort of crucial thing we've done in this paper is to sort of examine some of the fitting functions in the literature and see if any of them work for our case. So again, this is a ratio. Again, this time it's a ratio of fitting functions to simulations. All you need to know is that if something's close to 1 on all scales, then it's doing well. So we looked at 4 different ones. This light blue one, interestingly, comes from one of those early modified gravity embodied simulations that I mentioned right at the start of the talk. Sort of, I think it's a 2010 archive paper, and they do a fit there. But unfortunately for us, this fit fails for our case quite badly, actually. And the reason here is that in their simulations, they only consider a single value without any time variation. And that assumption is kind of carried with them into how they create this fitting function. And so sadly, because we've broken that approximation in our stuff, unfortunately, it means that this kind of fails quite badly. We then looked at halo fit. So in purple, we have halo fits. That's our standard lambda CDM thing. And this is quite an interesting case because conceptually it should fail. And the reason conceptually it should fail is that it's basically matching a linear spectrum to a nonlinear spectrum. And you get away with this in lambda CDM because you don't see anywhere near this much variation in nonlinear spectra from things that have a similar linear spectrum. But of course, we're explicitly kind of breaking that one-to-one in our case here. So halo fit is conceptually problematic, and yet, because we're in a regime kind of by construction close to lambda CDM, numerically it actually does okay. It's not a complete disaster.
Does halo fit work in lambda CDM? Because essentially the halo model is kind of you reach a certain density threshold and then you collapse. And so it doesn't matter how you reach that density threshold, just the fact that you did is all that matters. And that's why all you need is the linear power spectrum. Whereas I guess you were saying that in modified gravity, you might have different strengths of gravity when you collapse. So the thresholds will be different.
Yeah, basically a lambda CDM universe is really boring on some level, right? In that just your linear spectrum, you can almost match one-to-one with a nonlinear spectra. And it's not that wrong because the sort of universality you're talking about. I mean, you can write down halo models in these modified gravity theories as well, right? But just the lambda CDM is just like a simple limit. It's where we build our intuition. But of course, lambda CDM is very simple and we should never forget that, right? It's like the universe is tuned to make our life easy.
Yeah. That was one of your takeaway messages. So good to remember.
Yeah, exactly. But yeah, so then there's this halo model reaction approach, which is done by Matteo Cataneo and Ben Bose and a few others. And that has a reference lambda CDM and adjusts the reference lambda CDM according to a non-lambda CDM cosmology. And it's a really sort of clever idea that they've been showing some really cool results with. And so we tried applying that in our case, and that's the blue line. And you can see this is doing pretty well, actually. Of course, I'm just showing you, 2 snapshots from 2 simulations rather than 10 snapshots from 14 simulations, right? I'm not saying they're necessarily all this good, but they're not vastly unrepresentative either. And you can see it does quite a good job. So this is all very promising. So I'll just mention one more result, which is that this is the fitting functions for the matter power spectrum. But we also want to see how well the fitting functions capture the lensing observable, if that's actually what we're going to compute. And so we've done that here. So again, these are, ratio plots. So we want something that's close to 1. And again, we've got React in blue and then halo fit in green. And the interesting thing here is not only does React continue outperforming halo fit, it outperforms it by more for lensing than it does for the matter power spectrum. So I think what's going on here is that I said, well, halo fit is conceptually wrong, but numerically gets away with it. Lensing observables sort of integrate over a range of times. And so I think with halo fit, you sort of add up the errors when you do this because conceptually it's not capturing the phenomenology correctly. Whereas React, because it's capturing the phenomenology much better, as you kind of integrate over these range of times, your errors don't add up in quite the same way. So we think that's why the React performance is better relatively for the lensing than for the matter power spectrum. However, we have a bit of a but here, which is that one thing we do find is that React does a much better job of predicting the lensing observables for some of our simulations than for others of our simulations. We don't fully understand why this is yet, right? So what these 2 plots I've got here are essentially a best case and a worst case, just to give you an idea. So this is a worst case here, and we've put in these vertical lines. So React, in this case, allows us to get to 3 to 500 in L, something like that. And then in the good case here, we're getting to 3 to 4,000. So let's just put that into context on our lensing plot. So we have our linear theory stuff here that allowed us to go this far. And then in our bad cases, React's allowing us to get to about here, something like this. And then in our good cases, React's allowing us to get to somewhere here. So even in the bad case, it's a significant improvement. But one of the things we sort of like to do going forward is really dig into React and understand much better why it has this kind of issues. So that's sort of the main putting things together from the 2 papers. So we have this framework, and this framework kind of at least makes sense, and we have these checks that come along with it, but also we've now started simulating it. And I think that, these initial React results, and they are only initial results, they're looking quite promising. I think there was no need for any of this to work this well for this simple case and just taking something basically off the shelf. We have to modify React slightly but the way React has designed it, it's a relatively trivial modification. It very much makes sense to do what we're doing.
In Lambda CDM, I guess some other alternatives. You said that you can't run a simulation for every single cosmological scenario you want. So I guess some other scenarios people try in Lambda CDM is like these, are they called emulators, where you run like 500 simulations and you interpolate between them. I guess you could still do that here. You've just got a lot more parameter space because mu can be as time dependent as you want it to be. And if you're including space dependence, that becomes a problem. And then the other thing people try is this pseudo nonlinear stuff, like enhancements of second order of perturbation theory kind of stuff, where the simulation just runs super fast but isn't covering the full nonlinearity. Is that potentially doable in your case?
I think the answer to that, as far as I'm aware, is no one knows. So I haven't seen anyone do that, even in kind of these linear theory model independent approaches, right? Because in principle, once you go to second order in your perturbation theory, you should then have to start defining new modified gravity parameters, because these are really defined for this leading order setup. So as far as I'm aware, and I might just be missing some literature, I haven't seen anyone do that.
That sounds like something interesting. If you're watching this talk and you get the idea, you have to cite cosmology talks in your acknowledgements.
We've mentioned a couple of things where we might go next. We've said we want to understand React better for this lensing stuff. You asked about baryons, which is absolutely the right question to ask. So I believe there's some work ongoing with React to put baryons in it, in other cases, in like massive neutrino cosmologies and things like this. I've been told that work will be published soon. And so what we're hoping is to sort of join forces with those authors once that's done and try and, build something there that works for our simulations. But also you mentioned parameter space, right? And this is the other thing where we've got to go next, because we've done this very small bit in parameter space and we've kind of shown, well, okay, there's this bit here and React seems to do well, but that's why I call it's an initial study for React, right? We haven't validated React. And so the next thing to do is, so the Shankar, the PhD student at Manchester, is going to start really thinking about, okay, what's the parameter space we want to cover, and start kind of bracketing that parameter space with simulations, and then doing a sort of very, detailed validation of React. And because that's what we need for the data analysis. We need to know there's some significant range in parameter space we can go to that actually these predictions will work. The other thing as part of that, which I sort of skimmed over and didn't really deal with, so I mentioned halo concentration when explaining why you get so much difference between the modified gravity simulations. So actually, this is a known thing in React, that to get it to work best, you really need to understand the halo concentration in the model you're dealing with and adjust that, as well as just adjusting some sort of quasi-linear ratios. And so that's the other thing we want to do then. So as well as scanning over parameter space generally, also then dig into the halo concentrations in the simulations. And we're hoping that those things combined will really sort of validate React. And then at that point, you're ready to go. You get your Euclid data, you run your MCMC chains with this binned in redshift mu intervals, and you press go, and you hope you've got your baryons right that you're going to marginalize over, and then you see what modified gravity results you get out, and see whether, and of course the goal with this is to see if the data allows for any deviations from general relativity, right? That's the goal here, and so yeah, we're about, 3 steps on the ladder towards that.
I guess with the concentration though, you'd still need to come up with a model for how the concentration changes. Like if you want React to work entirely independent of the simulations, you can't measure the concentrations from the simulation as an input to React.
Yeah, I think our hope is that it should be similar enough to Lambda CDM that we can basically, interpolate in some sense across the, the range of parameter space we look at, and that should be doing something fairly sensible. And that's one of the, sorry, this is a bit of a tangent, but that's one of the advantages I like of this sort of approach is, of course, in everything we're doing, Lambda CDM is a well-defined point that we're kind of going around. And so all of the Lambda CDM machinery should work in the limit that we approach that point. And I think that's a practical advantage of this approach, as well as the philosophical be model independent approach.
Outside of your own research, what do you think is the most interesting thing in cosmology at the moment?
I'm going to pick the much maligned lesser tension, which is the sigma 8 tension, as opposed to the Hubble tension. Not only because, 8 is bigger than 0, right? So it must be the more important tension. But I think the thing is with the Hubble tension is you're not comparing apples with apples in some sense, right? The things that disagree are very, very different things. And so it's not clear to me how and when the resolution will happen. But sigma 8 actually is much, if you're comparing, basically linear theory weak lensing cosmology with linear theory cosmology for the CMB, you're much more comparing apples and apples. And so in that sense, I think this is something that should be much more resolvable on a shorter timescale. And it doesn't matter how it gets resolved, it has to get resolved. Otherwise, what we're going to do with Euclid, right? If Euclid comes out, and even if it is due to systematics as opposed to physics, if that's not recognized and dealt with now, then Euclid's going to have the same systematic in it, presumably, as the other lensing surveys that are finding this sigma 8. So I think I think people are too focused on the Hubble tension. I think the sigma 8 tension is really going to matter over the next 3 to 5 years, and it has to be resolved somehow.
Yeah. I guess there's still hundreds of thousands of years of evolution, but I take your point. It's a good one that because the CMB is not measuring H naught in any direct way, whereas it is measuring perturbations in a direct way. You'd still have to evolve those perturbations for a long time. And I mean, that evolution still depends on lots of different parameters in your model and this and that. But yeah. And I think sigma 8 is super crucial, right? And even if you want to solve H naught, because most of what were best solutions to H naught just make sigma 8 worse, which is not, it's not a solution, right? To just move your attention to something that people talk about less often.
Yeah, exactly. And yeah, of course, everyone wants the model that solves both, but then you solve both and find out that one of them was a systematic anyway, right?
Yeah, that would be a mistake, I guess, unfortunately. Cool. So thank you everyone for watching. If you like this, please do subscribe. And if you want to be notified, don't forget to click the bell. Click like to help with the YouTube algorithms, and share the channel with your colleagues and collaborators. If you have any questions or suggestions, please leave a comment. If you're a researcher with an interesting paper coming out soon, get in touch. And other than that, thanks again, Dan, for the great talk.
No, that's brilliant. Thanks, Sean. Cheers.